Welcome to Stochastic Processes, Lesson 11. In this lesson, I'm going to talk about birth and death processes, the classification of these processes, and then we'll talk a little bit about cues. So we're going to talk about birth and death processes. And the term here, birth and death, just stands for any process whose state rises or falls by one, where the transition time depends on the current state. So for example, customers joining and leaving a queue would be an example of a birth and death process. So we have some points here. State transitions are only of two kinds. A birth increases the state by one. A death decreases the state by one. In state n, births occur at rate lambda sub n, and deaths occur at rate mu sub n. Both are exponential and independent. So again, note the rate carries a subscript to n here. Unlike the Poisson process, the dynamics can depend on how full the system is because of this varying lambda and mu based on n. So these are some subcases. We have pure birth processes where the mu sub n equals 0. Nothing ever leaves, the state only rises. Then we have just the opposite, a pure death process where lambda sub n equals 0 for all n. Nothing arrives, the state only falls. Then we have the Poisson process, which we talked about in the previous lesson. And there the death rate is 0 for all values of n. And lambda sub n is just the constant lambda, as we saw from before. Then there's something called the Yule process, where the death rate is 0 and the birth rate is fairly simple. It's just n times a constant. So the birth process rate grows as the population grows. So a basic question is to ask what happens first, or what's the probability of happening first, the death or a birth. So in state n, a birth and a death are racing each other. Both waiting times are exponential and independent. We need the distribution of the minimum and which one wins. So we have a general theorem here, theorem 32 from my book, and I don't prove it here, but if you go under Wikipedia and look up exponential distribution and then scroll down to minimum of exponential random variables, you'll find a derivation of this. But let's read it off. If x1, x2 up to x sub n are independent and exponentially distributed with rates lambda 1 up to lambda sub n, then their minimum is exponential with the rate equal to the sum. That's what I have summarized here. And the probability, this is what we're looking for, and the probability that the minimum comes from event k is given by this here. So this is saying k goes first. Now in our case, we only have two random variables, right? The birth and death process. So it's pretty easy to apply this to our situation, which I do on the next slide. So for the problem at hand, we apply theorem 32 from the last slide with n equals 2, and that gives us the jump probabilities. So the probability of going from state I to I plus 1, in other words, having a birth first, is this ratio. Then the probability of going from state I to I minus 1, having a death first, is this ratio here. So each direction wins in proportion to its own rate. The holding time in state I is exponential with rate lambda sub 1 plus mu sub lambda sub I, plus mu sub I. That's from the first part of theorem 32. Then I just have a little diagram here showing these probabilities. You notice if you're in 0, you have nowhere else to go but up. You have to have a birth first. Then after that, these apply. You go up 1 was this probability, for example, and down 1 was this probability. And the ratios depend on I, on the state you're in. You notice that these are different as you move further along. On this slide, I want to talk about classifying the process, the birth and death process. And I have two results here. The birth and death process is recurrent if and only if the sum of this product here, these are the rates from the death and birth streams, if it equals infinity. So that's when it's recurrent. And positive recurrent, you have this condition and this quantity here. You notice this is not the same as this here. That's less than infinity. Now, if you have this condition and this is infinity, then you have the null recurrent case. Okay, so it takes a bit of effort to derive these, and I decided not to do it in my book nor in the slides, but I have a reference here, Karlin and McGregor. This is a paper, the classification of birth and death processes from 1957. So I can put this in the information to this video if you're interested in the details. Okay, so on the next slide, we'll actually use these results to exhibit an example. Let's look at an example. I took the formulas from the previous slide. This was for recurrent, and this was for positive recurrent, where you have less than infinity. And then if this is infinity, which it turns out to be for this example, you have null recurrent. So our example is lambda sub 0 is 1, mu sub 0 is 0, and then for n greater than or equal to 1, both lambda sub n and mu sub n are alpha times n. So we just plug those into this formula here. We get 1. So this is the product of 1 times 1 I times. And then you sum that up. And of course, if you add 1 to itself an infinite number of times, you get infinite. So this is recurrent from here. And then to check whether it's positive or null recurrent, we need to do the this formula here. And you notice this is like n minus 1. So that's where you have to go to, that's why you need these 0 terms here. So you get 1 over alpha, then 1 over 2, 2 over 3, because they're out of phase by 1 here. And then you notice the 2's cancel, the 3's cancel, the I minus 1 cancels with the term before it. And you just get 1 over alpha, which you can pull out of this summation, and then 1 over I. But this is the harmonic series, which we know is divergent. So this is equal to infinity, which means we have null recurrent for this particular example here. I slightly modified our example from the previous slide. I made the death processes a little bit faster, and as you might suspect, this will draw the process as a whole towards 0, and it may be positive recurrent in this case, or you might suspect that. And in fact, that's the case. I copied our formulas from a few slides back. This was for recurrent, this was for positive recurrent. So we do this computation first. You plug in these values, you multiply it out, you get a lot of cancellation, you just get I plus 1 here. And then when you sum from I equals 1 to infinity, of course, this blows up. So the process is recurrent. And then we want to do this here. And when you do this, the product, and you plug these values in, you get a lot of cancellation. I left out the details, but when you do this, you just get 1 over I times I plus 1. Then you break this into 2 fractions. And then when you sum here, the first term remains, but then the second and third term cancel. and the third and fourth term cancel, and so on out to infinity. So the only thing you're left with is the first term here, 1. You get 1 over alpha. Alpha is a constant, so this is less than infinity. So our suspicion that this change in the example will make the process positive recurrent is borne out here by our calculations. Okay, so now we have two examples, and on the next slide I'll give you the formulas for the stationary probabilities. The stationary distributions for a birth and death process are given here. This is for state 0. This is for state k, k1, 2, 3, and so on. If you're interested in the derivation, I'll give you a link to the Wikipedia article on where these are derived. What I want to do is apply it to our example. So from the second example from the previous slide. So we'll do this first. We already computed this. This is 1 over alpha. So you have 1 over 1 plus alpha, which is the same as alpha over alpha plus 1 when you do a little bit of algebra. Then if you take our formula from the previous slide where we computed this, it was 1 over alpha times 1 over k times k plus 1. And so the 1 over alpha cancels when you plug in this here. That alpha cancels with the alpha here, and you get this. And you can try it for an example. Say if alpha is 10, then this is 10 over 11. So the majority of the time you would expect the process to be in state 0. And if you put in alpha here, you get 1 over 11 times this. You could try a value of k. Let's say k is 1. Then you have 1/2 here, so 1 over 22. And it just gets smaller as you go further out. So the most of the time you're in state 0. And we kind of cooked it that way because we made the death rate greater than the birth rate. So you would expect to keep hitting back to 0. The MM1Q is an example of a birth and death process. The assumption is customers arrive by a Poisson process with rate lambda, and there's a single server that handles them with exponential service times mu. You can think of a queue in a supermarket. So there's an arrival rate to the server, the person checking people out, and there's a rate, an exponential service time for the actual, how long it takes to process each person. So this is a birth and death process. Arrivals are births. Service completions are deaths. Lambda sub n is just lambda. The initial death rate is 0. You can't service anyone if they're not in line, right? So this is 0. And then after that, it's just mu. And then what does this mean here? So the first M means Markovian arrivals, and the second M means the services are Markovian, and the 1 means there's one server. I think I explained this. Yeah, so that's an example of probably the most simple queue. I have a slightly more complicated queue on the next slide. Let's look at that. Okay, so this is the MMCQ. Now I'll allow C servers instead of 1. An arrival takes any free server. Full or busy, it joins the queue. The arrival rate is unchanged, but the service rate now depends on how many servers are working. So you have your arrival rate as before. The server, or the death rate, so to speak, is n times mu, when n is between 1 and less than c. And then, of course, when it's c or more, it's just c times mu, because you can't get any more processing beyond the C servers that you have. Okay, so let's continue. There's an actual notation here for different types of queues, which I have on the next slide. I have the Kendall notation for queues on this slide. This is the format. These are the meanings of each of these. So A is the distribution of the inter-arrival times. M stands for exponential. There's other possible values. Then S is the distribution of the service times again. M stands for exponential or Markovian. C is the number of servers. K is the buffer size. So you can limit the size of the queue and turn away people after the queue is so big. N is the size of the population of the customers related to the queue here. And then D is the discipline. So first in, first out, random order, and so on. There's different possibilities. So for the two we looked at, MM1 and MMC, if you wanted to do the full expansion here, the first three are right, and then you would have the buffer size is infinite. We didn't limit that. We didn't limit the population, so that's effectively infinite. So these two are infinite, and then we were assuming first in, first out. So this would be the full Kendall notation for MM1 and MMC queues. Some takeaways from this lesson. In a birth-death process, states move up or down by 1 at state-dependent rates. We looked at some special cases of birth and death processes. For example, the Poisson process only has arrivals, so it's a pure birth process. Then we did some classification of the recurrent, and we had null and positive recurrent, and we had equations for determining those. Then I gave you the equation for the formula for the stationary distribution, and I'll give you a link to that in Wikipedia. Then we talked a little bit about queues. I went over two examples. I talked about the Kendall notation, and then this last comment here is just related to the MMCQ. So for part 12, which is the last part in this series, and then there's a part 13, but it's not new material, it's just problems. So if you like this, please give it a thumbs up and stay tuned. In terms of the lesson 12, we'll talk about the Q matrix, and that focuses on the rates rather than the transition probabilities. And then we'll relate the transition function to this Q matrix. Diagonalization is a way of computing it. Stationary distributions and continuous time. And then I have a short retrospective on the entire 12-part series. And as I say, there's a set of problems after that. That'll be lesson 13.